this is the server, and this is the client. So when the PC sends the packet, the Ethernet will be here. So there is no problem. The kid will take this MAC, change the size, and then we send back to the PC. So you can have several PCs sending to the kit, and the kit will respond to the server, to the PC. But you will assign this here an IP. Suppose that's, and the PC will request which is your resume address. So to make this easier, because it's not you have to tell the PC this IP corresponds to that Ethernet, that is
the static IP table.
Yeah. So you need here an RP. So it's a very, very simple RP. So do you need to configure this?
Oh.
You can use DHCP also. So you can press the button here and will request DHCP. Very simple DHCP.
Yeah, okay.
Don't ask name server, don't ask anything.
But it's a well, solid part of the stack. So
Yes. So
it's all in a state machine. No.
there is no CPU.
Again, with the internet, similar to DDR3, the question is all the PHYs, but the PHY with DDR3 is inside the FPGA.
No. This is a complete module apart. You can use it or not. You are not forced. It isn't.
Sure, but
Okay.
you need an external PHY, or you don't. You just toggle wires directly from FPGA with this. Oh, this is hardcore. I thought that some external PHY would be.
No, it's all VHDL. I don't want to add any external file, or I don't want to add any third-party tool. That is, I don't want to use Python. I don't want to use any script language that generates.
So how do you connect actually the twisted pair wires? Do they go directly?
I need a feed. You know,
Okay.
yeah, yes, I need a feed. But all the systems need a feed. Microcontroller need a feed.
Yeah.
The feed is always in the feed. I cannot. Tell me.
Nije ostatak ekipa.
A ja sam mislila da stigla.
But I don't know if there are. I see somebody working on a 100 fee. The fee for the 10. Yes, you need a fee.
And I will also now give you the keyboard and mouse so you can, now you are in control.
Okay.
Oh, just okay. It can escape to my phone.
So,
In the kit there should be a fee.
okay.
And the fee. And here is the CPC.
Okay, and they talk via RMI or what is the digital interface between the five?
Yeah, this
RMI.
is, yes, but I didn't configure this. Most of them are self-configured. So they negotiate with the wire,
Okay.
and then you send it. Most of them, they send you the clock, and you use that clock as a reference to send the data or receive the data. In the case with Goran, the reference was, I think, So where is the
Down.
It can be either 25, 50 or 125.
and if it goes low, it will do that for you. That is, this is the clock, always. This is all from 1 gigabit. The same happens here. The pieces negotiate everything for you, so you don't mind. You only have to be worried about is that there is a transmission clock. You send the packet, the feed will do it everything for you. I think there are some cores that try to do this. As I'm sure there are for 10 megabits, no megahertz, megabits.
For 100 it's much more difficult.
And yes, there are some working. But if you have this, then you have to do the interface. So this is,
And the file is very cheap. I don't know.
yes.
Or not. You
Yeah.
have built in the file into the ULX4.
Yeah, we have like this 100 megabit, it's a microchip, and on gigabit I think it's a Ramtex or something. It's not. And now we have like the gateway. I think it's a Broadcom or something. So we have like 3 different parts.
And they more or less work with a similar IP or it's an
I
open-
think,
it's an open version.
yeah, I think no. How much difference is between like different pies, but pies with the same
No, they are
protocol?
But
they are
completely
very much the
different.
same.
Ah, they are the same.
Gigabit and 100.
Yes, you see it? Well, yes, 125 megahertz. But the only thing that you have to worry about is that you can match the frequency in the FPGA. Then all the protocol is the same. You don't need to do anything. So in fact, the whole core works for 10, 100 or 1 gigabit without changing anything. Only sending the data. So the fees are the files are in some way to 1 gigabit well thought. In the case of the Goran, we have to use double data rate because it has the half the data. So, okay, we want to start now?
Yeah, you can start. I think few people are missing, but we don't know if they will show up. Or
Okay.
How many people do we have who haven't seen anything about the ScopeIO? Just a brief.
maybe 2 of them didn't work much with the PGAs, but everyone else did work with the PGA, but you didn't see the ScopeIO actually.
I didn't.
No.
You didn't see it? You saw it?
I saw it yesterday, but
Yeah.
I didn't work it.
Yeah.
Did you see ScopeIO before in action or not?
Yeah, so we can maybe.
I showed the.
You have the
Ah,
mouse.
yeah.
You are in control.
Yeah,
Okay.
Yeah, so you can use another tab and all.
Yeah.
Enough. They saw nothing to it. So
Mhm.
maybe just
Yeah.
I know it's boring for most, but just a brief.
Yeah, no, it's.
Sorry, it's not English.
No, it doesn't matter.
Alt shift.
Okay.
Huh?
Can you
Drop
drop
it.
it? Where is the wire?
Зависит от монитора.
Epsilon is a Z, yeah.
But this is the last video. Well, this is an application. That is what is all this is a library where you can embed it your own design and then check the signals that are inside and see it in the output. So For example, yesterday you were presented the a design, and I see that we are sending data for debug. This data, in fact, it was an analog to digital conversion. So what you are trying to see is sending this data out, maybe then converting that to an analog signal and watching in an oscilloscope. So if they embedded their design with this, they don't need to do that. They capture directly those data and they can draw and see what is happening directly in the FPGA. So the library is for debugging your own design inside, not taking the signals out or finding trying to do something strange to get that. But this is an application to show how it works for the ULX3s. And basically what it does is taking the data from an ADC that is in the board and drawing the signal, and you can control it. So this is, in fact, it's an application that could be in another application. So this is what it does. You can control, in this case, you can control the whole system with the four buttons in the ULX3. And the limitation in this case are 8 channels, because the ADC in this case has 8 channels. And then you can control the resolution, also the time. Let's see, triggers.
So if I may try to summarize it. So it looks like an oscilloscope, but the idea is not to make just another oscilloscope, but a tool so here you are showing the ADCs, because this is just an example, but the cool thing is that you can correlate internal stuff from the FPGA that you otherwise don't see, which is hidden well within FPGA, and especially at high speed, it's difficult to capture the data in moment, and that's what the tool does.
Yeah, we used it many times for debugging our modules. So you just put the module inside of the ScopeIO and you debug the module. So any signal, you can just point there and it will show it on the screen. So I think Emil used it to get USB host working.
No ScopeIO, no USB from Emil.
So of course, the FPGA vendors are pushing their own embedded logic analyzers. In the case of Lattice, I can confirm it never worked actually at all. And in case of Xilinx, it works, but it will crash your running frequency significantly and has significant limitations. So yeah, that's the idea. Use this as an embedded.
Yes.
Where you have the full control.
Yes.
It's not what is now you're showing.
No. This is why I always try to do emphasis. This is an application. This is an application because if I tell you that this is a copy or is a, and what is this? For what is useful? So this is the simplest case that you can say, at least a ScopeIO inside the ULX3 would be useful as an oscilloscope. Yes, but it's not the main application. This is one of the applications that you can use. So the main reason to do this is that I can put this inside the FPGA with your design, take all the signals, and then send in, for something that is simpler, because you have an output of the a video that you can always connect. So instead of having a lot of signal, you have to connect or in a logic analyzer or in an oscilloscope. In an oscilloscope, you have maybe 4 to connect, plus the cost of that you have to do to connect all the pins correctly, found the ground system.
But you cannot at high speed. This will work maybe to 25 megahertz.
Yes.
At 50, there,
Yes.
and you want to debug at 1 gigasamples.
You don't have any problem. You can go as fast as the FPGA. So this is the main reason. So what we have here is the application. No, this is not. This is not that. No, this is a ScopeIO specifically for the ULX3. We try to find something that I think maybe you work and we have in common to see how you embedded the ScopeIO. Try to see the main block first. So this is the communication. So this module can be added, for example, if you want it at the Ethernet, you replace this with the Ethernet, and that's it. So you have all this done. This case is the USB. You plug the ULX3 to the PC, it will recognize automatically, and you can control from the PC. This is the controller for the buttons. Yes, and that is it. So we will jump it. These are and this is a ScopeIO. So this is what does everything. So what you have here is the controller, that is the input output. This is the clock that is will be the clock of the USB, the clock of the WARP, the asynchronous system, or the clock of the Ethernet if you want to use UDP. This is where the data input comes, and this is the data that you send back to the PC or to the controller. Then you have the input clock, that is the data, how fast it's gonna be. The enable, that is, you don't always want to send a sample with the clock. For example, the input clock here is the clock that controls the ADC of the ULX3, but it is a serial communication. So first you need to collect all the input data, and when that input data is ready, you enable it. And then you have the collection of samples. You don't need to tell you nothing else from here. What it comes next can be avoided, but I will tell you. This is the controller, but the controller of the DRAM controller. So you want to take the data that you capture and you want to send that to the RAM, to the synchronous RAM. So you are going, if you can store there, the thing is at 32 megabytes, you can store there all that samples, and then you can dump it. So you can go faster than the link. Maybe the link is slow, it's a synchronous system, but you can dump all this data in the in the DRAM at high speed that that DRAM can go up to 250 megahertz, and then when it's full, you can dump it, the whole system, and you can start in the PC if you want. It's okay? So, if you don't need the DRAM, you don't add it. You can avoid it. So, but it is connected. And then comes the video clock. So the video system. So you have the video clock, the pixel, the horizontal, and the frame and the video blank. These are needed to generate the digital system. And that's it.
And can that also be avoided if you are controlling it via Ethernet? Can video be avoided?
The video, yes. I am working on that. That is.
Okay, so the video is not.
No, suppose
video can be plugged out.
Yes. Suppose that you want to dump all the data in the DRAM. So that's your main goal. And you don't want the video because the video is expensive.
Yeah.
So what you don't have, you can avoid it. You don't need it, as you can avoid it the DRAM. You don't even need to connect this. That is, VHDL force you to connect things that are even if you are not going to use. So, if you can see, the only thing I have there is the frequency of the DRAM, the video, it's the video parameters that you want. This probably is gonna be here. Now we are see how this works, and nothing else. Now the main part is this. And you will see something that maybe is weird, but familiar too. This is layout. This is how you configure everything. Yeah? So, take into account this. This is a string. Yes? So this is VHDL 88 compatible. It's not something strange. So it's very old, it's compatible.
So just a short interruption. How
Yes.
many people in the room have actually tried to process strings in VHDL? I mean, VHDL is very hard and difficult language, and processing strings in VHDL is a pain.
I have tried, and but this is something like a number 1, 2, 3, 4, 10 to concatenate. Doesn't manage to explain.
Doing this in a variable length is really. If what I'm seeing is that the strings are not of predefined width.
No. The compact, this what it does is deleted all the space. It's the only thing that it does. Because it makes the synthesis tool faster. So to see how compatible it is yes, it's compatible. Vivado is compatible. Quartus is compatible. HDL is compatible. And
Lattice.
Yes. It's not sure it's not to be here. None of them blame. None of them complain. It's working. So why I do this? First of all, defining a structure in VHDL is very painful. Yeah. One thing. The other thing that convinces me most is the variable length array that I cannot put in a structure. That is, VHDL requires you that the vector must be fixed. And also that this structure is always the same. So for example, suppose that I don't want to define a color here. So I don't need to add it. When I look for this, they will tell me that it's null, and I can use, then I will show you how can I set a default value. So if something there doesn't exist and you want a default value, you can add it. So this is the way that you can control a ScopeIO. Although you don't need to define all those stuff, only the things that are required. You only require a display, a number of segments, and for example, if you don't define the waveform, you don't have video. So it will detect that this is not here, and it won't generate any part of the video. So here, yeah?
Can you stop a little bit?
Yes.
Just scroll one line above. So how many, so for example, line 153, how many people in the room are recognizing the natural image 32 times 32 plus 1? Who has seen this before? Okay, so
Even I haven't seen.
I have seen it, but I'm avoiding it. So
Do
this
you
is
want
the
to explain me this?
Yeah, the line above, the conversion from width and height. Exactly this. So then go to the right.
This much.
This is the conversion.
Yes, this is VHDL 8080. What it does is you have to tell the type, and then you have to tell the image. What you put here will be converted to a string.
Okay, that's it.
So this is a string. When I use this and concatenate the result of this. So, for example, the input here comes from a kind of backward compatibility, but I can set here the number 4 and then take the parameter. We will see how we do it. So if you want to control anything from the ScopeIO, you can do this from here. I think is in some way besides these structures that maybe for many of us the first time we see it's what is he doing, his guy? What he built? No, this is VHDL. It is used for. Have you seen the assert statement with the report? Well, this is for the report, but it works. The weird stuff here is this string and how it is parsed. Yeah? But how it is parsed from the user point of view doesn't care. What you want is how to use it.
So, if I may try to echo what you're saying back. So this maybe look weird and ugly, but this is actually much more natural and time saving compared to defining all those parameters in true VHDL. And this is saving time and nerves, I would say, because in VHDL, well, you couldn't avoid any of the parameters if you would be doing this in pure VHDL.
Yes, also my problem was that first of all it could be a collection of parameters that you have to add in the generic, and you have to explain, and you have to, and for the user will be scared when they see that. And if you don't want, why should I have to describe it? Even if I had a default parameter, sometimes I cannot add a default parameter. For example, in the DRAM, the address and the data will have. I cannot exactly add a default parameter. So. So I was trying to. This is pretty much similar to JavaScript. I don't know how many of you have seen JavaScript object, or maybe it's also known as JSON. I don't know. This is JSON. So there was a guy that was writing something in JSON. They claimed that it worked. When I went to see if it worked, it didn't. And what he was trying to do was parsing a JSON inside the HDL, not taking the parameters to use inside the definition. So I had to write my own. Anyway, what we want is to know how it works. So all the things that are here that I don't want to use it, if one of those parameters is not defined, okay, there will be a default value. Or as Marco was asking me, I don't want to use the video. I only want to use the DRAM. So don't define the waveform. And that's it. So all the things that you are looking here is a controller of the ABC. So that would be the embedded system that you were. Is the equivalent to the embedded system that you want to debug. But once you have all the data that you want, you set it here as I showed you before, and then that goes to the ScopeIO by that the one that really does all the job. So here are the boards where ScopeIO was ported. So all of these are kit dependents. And what is portable is here in library. Here this is ScopeIO, and this is the entity. So now you will see some strange thing, but don't go. You don't have to know anything. So this is to define for the this is for the DDR controller. So you don't define, you don't have to worry about. All these parameters are not defined by you, but the only thing that you have to tell is, I want this DRAM, and it will do everything for you. So the DRAM can be a synchronous RAM, a DDR1, a DDR, DDR2, DDR3, and if you don't want any of them, it will define some default value that won't bother you. So let me show how you extract a parameter. So here are the number of inputs. We were defining the number of inputs in layout. This is not needed. I use it to emphasize that this is that string with JSON, but it doesn't need it. And then you have this double star. I don't know how it's called it that way, or you call it asterisk. So you know what this that do in VHDL?
No, I don't know.
Okay. No, but you know that this is the power.
Okay.
Yes, but you can overload this. I use this because it's a operator that has the most present. And suppose that you have a variable and you want a member of the variable. So you use this, the point. Well, the asterisk does this, the point, that it selects the member. So what I do here is asking is the input member of layout. This is what it does. And it resolves and returns me the number 4. So as I have this operator overload, with integer it automatically converts the string to a natural number. So this is how I get the parameter.
Okay, and the magic is the definition for overloading this double star, and that is what we don't want to see.
Yes.
Or maybe
I can show you, and then you can tell me, no, it's enough. I can show you. That is no.
Okay, so once again, because I'm starting to get lost. So, for example, this line 143.
Yes.
Your magic operator will extract from the JSON magic, will extract whatever the inputs has been described in the string and convert it to the appropriate type for the real VHDL signal or constant. That's magic. Okay.
So the signal is the constant waveform. So what I say asking what I'm doing here is taking the whole waveform parameter. So we are asking this for waveform. If you don't define the waveform because you don't want the video, this is a default value. So it will fill waveform with none. So I want to show this, and then we will go up again. So here is a generate. If waveform is different of no, it will generate a video standard. So you don't need to fill the other stuff. If waveform is defined, you can see that it's extracting the grid width. See? So that is waveform has inside grid, and inside grid has the height. Waveform has the grid width, and you get the width.
Okay, and what you are saying that if waveform is
Defined it.
is defined as none, is defined as none, then none of these tools that you mentioned on the board will go inside your expressions and will not attempt to evaluate it, because in that case, if waveform is none, then probably grid height is not defined at all. And it will just skip through this and not throw any VHDL typic errors which you...
And I tested.
Yeah. Okay, that's nice.
So this is the way I fell in love with this. So this one with this time, because it really helped me to started to say, oh, okay, I don't want this, and I want this. See? I don't want the grid. So if I don't want the grid, I don't define grid, and that's it. I will add the known. If I don't define the grid unit, it will be 32. So I don't need to do that. So do you follow me with this, Jason? Because now will be easier. Now we will focus on the ScopeIO itself. So all the things that are here has to do with the DRAM. If I define the DRAM, so here you see, if this parameter is defined, it will get the value. If it is undefined, that is the RAM wasn't defined, it will set it from 1. But this is the default value to avoid filling. So in this way I can define the size, because VHDL is asking me that in the entity this has to be well defined. So it's a trick. So the user doesn't want to use a DRAM. He doesn't need to know anything about that part of ScopeIO. Well, the serial interface. The serial interface, look, what it does is receiving what comes from the USB, Ethernet, or whatever interface. We have 3 for now: the asynchronous interface, the USB interface, and the Ethernet interface. So you connect it directly. There is no problem, and then it translated into registers. So there is let's say a variable length register where you can send data. So let's see that then. Then you have the trigger block. This is where you do all the no, this is a trigger register, doesn't matter. We see. And this is the trigger block. So as you can see here, you have the input clock, input enable, input data, and when you're going to shut. This trigger is a trigger shut, that is, there is a condition inside the trigger, and you find that condition, and you will tell the system that it has to capture the data.
Okay,
This
so trigger shot is the actual output.
Yeah,
All the
actual
other
output,
things are
yes.
inputs.
Yeah. So the input code would only be used to capture the data in the block run, and to trigger the capture. That is a shot. So that's the only speed limitation that you are going to have. Then it's everything at the speed of the serial interface or the speed of the video interface. That is your custom. That is, if you have a combination of condition with the input data, you will decide what is what you want, and you can trigger. There is nothing special about it. Then it's the waveform. And what this does is converting the serial interface into a parallel data. The serial interface is something like this. It's 8 bits. The first is the register number, for example, let's say 160, then the size, you have always to add 1 or subtract 1 depending how you see, but if this is 0, that means that there will be only 1 byte, and then comes the payload. So this is simpler. So if you need something with more bytes, you only need to change this. So for example, for a trigger, you don't need more than 2 bytes. This is more than enough. If you want 3 bytes, you add 3 bytes.
So, excuse me, what is this data used for?
This is for controlling those registers.
Okay.
So the first is the register ID. Then is the length. Yes. And then is the page. So what I was saying that if suppose that this is the register ID for the trigger, you don't need more than maybe 2 bytes, and then you have 2 bytes for the trigger. Yeah, but you can define the size that you want. Again, this is custom. If you don't, there is nothing there that is predefining. The CO clock will send you the data that you ask. So this system, what it does is taking these bytes and decompose them into parallel data inside. So everything you can control in this way.
So the trigger unit module has internal registers, and we are somehow addressing and filling or reading, writing these registers.
Yes, the register is
In real time.
In
real time.
Not
Yeah.
in synthesis time.
That's how we can set the trigger to change the level, to change the inversion, and so on.
yes, it's in real time. Here is register. This is for the game that is changing the size of what you see in the screen, changing the size of the signal. This is the register for the trigger version. So each of these has a register ID. The register ID is defined in a package, so you can change it. But it's well defined. We'll see then. Well, one is trigger. This is a storage where it's a block RAM with all the sample data. There is a time scale and a time offset. This is what controls what you see. And the time scale that is, if you have this, and yeah, then maybe you are sampling it, you won't have any problem if you sample enough fast. But if you decide that you want to compress this to see more, what will happen is that maybe you get this sample, maybe this sample, and this sample. So you will see something like this that is not real. So what this system does, when you want to compress the time scale inside ScopeIO, because if you are subsampling the ADC, ScopeIO doesn't know that. So you are telling the ScopeIO that you want to compress the data, and it will take from here to here, we'll find the maximum value, and we'll use that with the same here. We'll take the maximum value, and what you see is something that goes high and low. So what is useful for? Sometimes you have a digital signal. The digital signal is very thin. Yes.
How do you know the boundaries when you have to
You don't
go
know
high
it.
and when you have to go low?
No, you don't know it. So you have to do the maximum and the minimum
Okay.
every time. And you have to keep the maximum and the minimum of the past.
Okay.
And then you select which is the one that you want. So why is this useful? Because maybe you have this, and a long time then you have another of this, and you want to see the period of how many of these are. If you start compressing, it will disappear. So if you try this in the ScopeIO, suddenly you will see that you are compressing, but you always see one vertical line, and you don't lose the. So this is why it's need the time scale. Time offset is because one to go back and forth. The trigger mode has to do more with freezing or triggering once. Yes, it won't tell you if it has to, if it will trigger the positive edge, negative edge, or another thing. It has to do with if it is free, that is, you can see the video refreshing all the time. If you want to freeze one, or you want to trigger one, I stop. This is the only thing that it does. So this is the capture system, and this is what comes next is the video system. Time off, the time scale has to do with the horizontal and vertical line. Video address will tell, because you have, let's see. So this is a blockgram where the signal was stored, and you want to represent it. So what you need is to know if you are, and this is the display. Let's go low. It's better to do this to understand that this is display. So we are here. So this is the X of the display. So you are going to take this, and then we'll take this to represent one vertical segment of the signal. So this is why I need the video address. So it's telling me which position of the horizontal line the video is. So it's captured. So everything that is drawn in the video is done in real time. I don't need to storage this in another buffer. What I'm doing is taking this, and at this moment I will define with this two sample I will decide with these two samples if you have to turn on or off this pixel. Follow me? Yes.
But you're keeping the one line in the buffer.
I am keeping the signal,
Okay.
not the one line. I don't have any video,
Okay.
only the one. What I do is, which is the sample that I have here,
Mhm.
which is the sample that I have here. So,
But
do
you
I
have
have to draw?
You have to look at this biram as many times as you have the lines.
Yes.
But it's only one biram for the entire
Signal.
signal, and not each line that occupies additional memory.
No.
So can I understand that you actually don't have even a single line of the buffer for the video? Not a single line.
That's really hardcore.
No. Remember that chord that you don't like the name? Align? Somebody said, why you said that one? I changed the name. I put it later. But that chord, what it does is, because I have the counter of the video here, and so I comparing this, and the best way is compare and go to the register, because it's not as slow. So what I have to do then is to delay all the video signals to then get out of the video. So
But
there
it
was
doesn't matter because you don't see that delay. It's only the delay when you are delaying the video signal. You can
It
delay
has
as much
yes,
as
because
much as you want.
you are not paying. Entonces, so I have a serial register, and this because latency, and this call what it does is it's like you have the 0, the 1, the 2, the 3. In fact, it's a vector. You can tell this, I want 4, here I want 5, I want 7, I want 6. You tell this through the generic parameters. So this is why I was calling it align, because it was aligning me the signals to get the video. Now I call it latency. I think it's better.
So actually is one top of the pipeline coming out.
Yes.
So,
It's align.
I didn't look at this code, but actually, so you are having a variable latency delays for various stages of the signals. For some signals, you have to delay really long, but some are already delayed through some arithmetics or whatever, and then you have to delay them a little bit less. And some are so slow that you don't have to actually delay them at all. But they all have to come out of on the video
Yes.
order at the right time synchronously without any clock.
Exactly.
Crazy.
So this is okay.
How actually did you organize this latency? How did you, how can I say, organize the code and programming for everything to, or you just insert enough time of the delay to match them?
No,
to reach
I
the-
try to count. I have done.
Okay.
At the moment I wrote the legacy code, I was counting. And then I saw what's happening in the image, and I say, okay, I need a little bit more.
Well,
Because it's really hard to do in simulation. You have the serial bits out, and it's better to see in the video. That was really hard, and it doesn't take so much time.
And Miguel, if you will need a break, just let us know.
I see.
Because it doesn't maybe well. How long are we now?
1 hour, so maybe half more, then
Okay.
we can take a break.
As you want. If you want, we can
Yeah.
cut here and.
no, I'm still concentrated.
Okay.
Everyone.
Yeah.
So, we have the address, the frame. The frame is when starting new frame, so I can reset the counters and all that. The data value, that is a delay signal, because I have the address, I have the frame, I have data, and I have to tell you when that data is valid. The video clock the video pixel, that is all the colors and everything that is ready to be out for the DVI. And that was something that the board and Goran asked me for the
Box 3.
level 3, and the sync signal, the video on, blank and sync. So this code does all the work for the video output. So we have here maybe 3 important.
Yeah, for us, it was important that we get, like, we will send a video signal and we want that ScopeIO is aligned with us.
Yes, this is, we have the storage. The storage will be always there because we want it for capturing to the DRAM. We cannot go to the DRAM faster than the block RAM can. If you are sending to, that is what is because of the cost of addressing the DRAM. So this is a kind of FIFO, and when the FIFO is getting full, it's sending to the DRAM. It's a streaming. So we have the storage, we have the trigger value, and we have the video system. The amplifier controller should be south side. Yes, it's here. Should be move inside here. This is the latest code. And this is the internal architecture. Then it comes this is the DDR DRAM system. Again, if the DRAM system is not defined, this is not done. This is the data stream to send to the. I can explain this, but it's really hard. Yeah, it's a little bit longer because that is. I will tell you how more or less work. Seems better if I. We have the data coming, and this is the FIFO. So the FIFO fills, and when it gets a watermark, it triggers the DRAM. So when this happens, there is a DMA system. So this will request a DMA system. It writes the address to the DRAM, to the DRAM core. And this access the DRAM. This is how it works. So when you capture, you have two channels for the DMA. One is for the serial input-output, that is, you can dump the data to the PC to study it, and the other one is the FIFO that is writing to the DMA. Do you want to see the code? Yes, I think so. Just tell me if you see something that.
One thing that is maybe lacking in the code is if you could tell us about your convention. it's impossible to decipher which signals are inputs or outputs. That's the problem not of your code but in VHDL in general. So do you have? I see that you have blank lines between some ports on the not in signal declarations, but when you connect the port of an entity, you have some blank lines. Are those annotating and the
No. When those lines,
how do you distinguish if you don't have them in your mind which signals go in of an entity?
because what I try to do is writing the input device to the output device, and I said if it is, for example, here is capture controller data out. So that means the data out of the capture controller. I don't have, I think I've made probably, I have one of the worst variable name conversions. The problem is, if they are too long, the code is too long to read. That's one of the problems. So I try to have, in some way, saying, well, this is the capture control data out. So this is set. The capture controller is output the data here. So I use this. This signal should be connected to the controller data output. And then, if it has to go inside, I think it's better if I, sorry for this. So here I use the controller data output and I send to the controller data input. So this is an input signal that is in the controller.
I was just hoping that we could, when I look at your code, deduce this from just blank lines, but wrong guess.
What did I wrong? What did I do wrong?
No. I mean, everyone has its own coding style. It's actually quite clean from what I've seen, and my code is definitely not any better. And I also am not annotating properly signals in terms whether they are inputs and outputs. And just observing that in such a huge code, it would be easier to know upfront, maybe from a comment, which I also don't have. We rarely have comments in our code, so it's a common problem. But as the project grows bigger, well, knowing those things upfront maybe could help. Just as a suggestion. I have no idea how would I do it in my code, because as you said, it's always ugly. The more you add craft on your code, then you don't see the code, and it's hard to say
Yes,
where
I
you have
understand.
hit the sweet spot.
Yeah.
You know what I will do, a small comment and the arrow. So arrow pointing to the right and to the left. So the direction of the arrow means direction of the signal.
Yeah. So let me. Someone sending me message. So yes, this is quite complicated. It's not that I polish. When I code, sometimes I don't know what I am looking for. And it's a problem because if you think from the point of view of engineering, you are spending more time polishing the code, maybe instead of coding new code. So you have to have that in mind. It's a really complicated decision, especially for me. So I try to find those kind of things. That is, this is something that comes from the device, and this is something that goes to the mirror. to DMA. So this is the DMA controller. There are two different things. One is the configuration. The configuration takes the address and the length. So you can go at lower speed. It's synchronizing inside of the core. And then you have what is called to the controller, that you have to go at controller speed, to the RAM speed that is higher. So we want to have two different clocks. One are the negotiation for where what will be the next address and what will be the length that I want to transfer for each channel. This controls the DRAM core. Okay, this adds some latency. This is how it works here. The size of TI and TO is this, and the latency of each bit of this is 4. So you are telling this. So this is how you control. If you want, for example, the name of the generics are not the best. When I was coding this is what I chose. T0 has a latency of 4, T1 has a latency of 5. You can set it to 0 and will be a wire. Those latencies that I am adding here help to improve the speed, because it connects directly to the DRAM core. No, connects directly to the DRAM core and the DRAM. So if the wires are too long inside the FPGA, you will have problems with the speed. But if you add those latency, it breaks and you can go faster.
It's a little bit absurd, but the latency is speed, but it's true. Especially if the device is overcrowded and routing is already constrained.
And this is the controller itself. This is the DRAM controller. The EST has to do with synchronous data RAM, not the speed, because all SDRAM, DDR, DDR2, and DDR3, and DDR4 are all of them are synchronous speed. So it's a name to be a generic one. What you have to do is only to pass the frequency, the data. The data tells all the parameters of the DRAM, and the feed. Remember what I was telling you about the different kits that have latency. You pass this here, and then you connect. You tell them the parameters of the DRAM that you are going to use. So those parameters are chosen depending on the version. For example, for a single data array, you don't need AL, and you don't need this, and you don't need this. So you don't need to specify if you are doing the for example, for the ULX3. We will see how you have to. Let me see. As an example, how this data is defined, you will see that when I in the ULX3 entity, you will see that I only tell the chipset, the chip of the SSD RAM. I don't do anything else.
So you have some kind of database micron, Ringbond or something.
Much better than they are in the first one. The first one is really understandable. And then the DRAM controller connected to the feed. So the DRAM controller doesn't know anything about the boxes, the basic blocks to connect to the that you have to connect in the eFPGA to communicate with the DRAM. This would be the feed, and this is the controller, and this is P5. So here there is a special block for each eFPGA, and also it's not that it's manufacturer dependent, also is family dependent inside the manufacturer. You have one for the Spartan 3, you have one for the Virtex 5, you have one for the Arctic 7, and in the case of Lattice you have the ECP3 and you have the ECP5, and they are different. They are not using the same one. The ECP3, I try to find the difference, and the ECP3 is faster. I can go 500 MHz with the RAM 3 and have more serial lines. So if you need to, for example, you are working with you are trying to do a GPU with 16 PC lanes, you are going to need an ECP3. You cannot do it with an ECP5. They are more expensive, and I use this. Well, you connect this to the feed, it's connected to the feed, and that's it. So this is how it is structured block ScopeIO inside.